Well, thank you for taking the time today to spend a few minutes listening to this presentation that we've titled New Looks from an Old Herbicide Again. My name is Aaron Hager. I'm the Extension Weed Scientist here at the University of Illinois. And the focus of the conversation today is going to be around looking at some of the challenges that we face with respect to resistance to some of our soil applied herbicides. And the good news, I guess, is that we still have herbicide options that can remain effective and give us several good weeks of residual weed control. Now, if we go back into the not too distant future, it was very common to see scenarios like this, especially in soybean fields, where it almost seemed as though it was near impossible to not control emerged water hemp with glyphosate. It was a very, very effective product. Generally speaking, if the plants got larger, all we really needed to do was add more to the tank to still achieve a very high level of weed control. But unfortunately, as most everyone is aware, then along came herbicide resistance. And with the herbicide resistance came outcomes like this that unfortunately are fairly common today. We really have jeopardized the efficacy of many of our foliar applied herbicides in terms of trying to control the water hemp complex that we have. Now, clear back in January of 2008, this was actually the first year that the weed science program here at the University of Illinois actually came out with very specific recommendations on managing a particular type of herbicide resistance in water hemp. And actually back in 2008, when we first started launching these presentations during the Corn and Soybean Classics, we had designed these recommendations after we found our first instance of glyphosate resistance. That was about 2005 or 2006 in Fayette County, Illinois. And so after a couple of years of field trials, we felt like we had a pretty decent idea of how we needed to structure these recommendations. And back in '08, there was actually a 5-step recommendation process that we presented. And the focus really was trying to convince folks that you really need to do all 5 of these steps and not just pick the ones that you want to do or can easily do and ignore the rest. But what a lot of folks didn't realize is that even though we titled these Management of Glyphosate Resistant Water Hemp in Soybean, they were structured actually to take into account what we knew was happening in the background. And what we knew was happening and going on in the background was that the evolution of resistance to the foliar applied PPO inhibitors was increasing at an alarming rate. And so again, we tried to build these recommendations to be more or less holistic and encompass everything that we could think of to really slow up the evolution of resistance. And now, when I first would make this presentation back in January of 2008, when I got to this particular slide right here, this was a pretty difficult one for a lot of people to accept, because not only were we encouraging people to use a soil residual herbicide in soybean, we were encouraging them to use a full labeled rate. And if you think back to what we were doing back in 2008, that was one of the first years where some people were experimenting with what they were calling a setup rate of a residual herbicide. Basically, put out a little bit, try to buy you a couple of weeks of control, and then come in and spray your glyphosate and clean up everything. As it turns out, that was not a very good and effective program because, again, the evolution of glyphosate resistance was actually occurring fairly quickly. But a lot of people didn't like this. We basically heard about every possible reason why that soybean farmers didn't want to do this. Number one, of course, well, if we add a residual herbicide, that's going to increase my production costs. Number two, very common, well, that's just the university trying to scare us. It really can't be that bad. And then number three, well, we're not going to do anything different until glyphosate doesn't work anymore. And certainly by that time, somebody is going to bring out something new in the marketplace. So if we think now to where we are at today, I think the use of residual herbicides in soybean is not uncommon anymore. And it certainly isn't based on the recommendations that we were making at the time. It's simply the fact that biology is driving more and more farmers to use residual herbicides in soybeans. But we do have resistance to several of our soil-applied soybean herbicides. For example, on this chart, we have the herbicide groups listed in the left-hand column, and then whether or not that we've identified resistance in water hemp in the right-hand column. And so the group 2 products, things like the ALS inhibitors, very widespread, very common to have resistant water hemp. Our group 14 herbicides, the PPO inhibitors, things like sulfentrazone and flumioxazin, the answer is yes, we have resistance there as well. Our group here just about 2 years ago announced the discovery of resistance to what we call the group 15 herbicides, the acid amides, things like S-metolachlor and acetochlor, dimethenamide, peroxysulfone. That actually was the first report of resistance in a dicot weed species anywhere in the world. And then finally, the group 5, the photosynthetic inhibitors. And we do have resistance in Illinois water hemp, and we don't. So that is a yes and a no, but what in the world do we mean by yes and no in terms of group 5 resistance in water hemp? Well, it comes down to this. We typically use 2 different types of triazine herbicides in Illinois. We use things that are called the symmetrical triazines as one group, and we also use the asymmetrical triazines. And the term symmetrical refers to the arrangement of the nitrogen atoms around the phenyl ring. So if you look here at the structures of atrazine and simazine, you can see that the nitrogen atoms are symmetrically distributed around that ring structure. For the asymmetrical herbicide, which is metribuzin for us, we see that those nitrogen atoms are not symmetrically arranged around that phenyl ring. So all 3 of these active ingredients, atrazine, simazine, and metribuzin, we can actually use in corn, but only metribuzin can be used in soybean. So how the triazine herbicides work, and this will really become more important as we talk about resistance here in just a few more slides, but the triazine herbicides block the photosynthetic process. They actually bind at what's called the D1 protein in the photosystem 2 complex. When they bind there, they effectively shut down the flow of electrons that takes place through the photosystem. And some of the byproducts of that electron flow being shut down are very, very damaging to plant membrane systems. So the D1 protein is where these products work. Now, we said there's 2 types of triazines that we rely on here. There's also 2 types of triazine resistance mechanisms. And the first one actually was discovered clear back in the year of 1983. And what was discovered there was that there was a single change in the coding sequence of the target site D1 protein. And that single nucleotide polymorphism that was discovered in 1983 was sufficient to render high levels of resistance to the triazines. This is what's called a target site resistance. There's been a change, a physical change in the herbicide target site, so much so that that herbicide can no longer effectively bind at the target site and can no longer effectively shut down whatever that process is. The other type of resistance that we see to triazine is what we consider non-target site. So in target site, there's been an actual physical change to the target site that alters the herbicide binding. But in non-target site resistance, it's quite possible that the target site has remained unchanged, but something else has taken place that now renders that herbicide ineffective. And it's a little bit difficult to see on this graphic, but non-target site resistance could be things such as reduced herbicide absorption. If we simply can't get a sufficient quantity of the herbicide into the plant, we can't control the plant. There could be a difference in the translocation or the movement of the herbicide inside that plant. It may be restricted. That herbicide may actually be sequestered somewhere away from its target site so it can't effectively bind to it. But the one of conversation that we're going to develop and discuss further today is what we call metabolic herbicide resistance. And in metabolic herbicide resistance, what happens within these resistance plants is that they now have mechanisms in place that allow the plant to effectively and efficiently metabolize or break down the herbicide to an inactive state before it causes any damage or much damage to the plant. So again, in target site resistance, there's been an actual change in the target site, but in metabolic resistance, the plants now have the ability to metabolize or break down that herbicide before it can cause a lethal effect. And we can actually look at an example, a couple of examples of metabolic resistance. And this is actually atrazine metabolism in both sensitive and resistant water hemp. And so the way that we'll look at this particular graph over here on our y-axis, we have percent of the parent herbicide remaining. The parent form of atrazine is the active form. Along the x-axis, we have time in hours after treatment. So here at time 0 is when this experiment started, and all the atrazine was in the active, the parent form. And if we look at this line first right here for corn, what we see is that corn can very quickly metabolize or break down atrazine. It takes less than about an hour for it to metabolize half of the atrazine. And this is why corn is very naturally tolerant to atrazine. It breaks it down very, very quickly. Now we can contrast the corn line with this top line, which is a sensitive water hemp population. And as we can see, it metabolizes atrazine very, very little. And as it does, it's very, very slow to metabolize it. But the two lines here in the middle represent two different resistant water hemp populations. And we can see that they metabolize atrazine more similar to corn than they do a sensitive water hemp. So with the ability to metabolize the atrazine this quickly, the atrazine essentially is not lethal to these populations. Now this is not atrazine resistance, this is actually group 15 resistance, but we see a similar mechanism or a similar metabolic basis for this resistance. Here we're looking at the amount of time it takes these various populations to metabolize 50% of the absorbed group 15 herbicide. If we look in the center column labeled DT50, this is again, the amount of time it takes these populations to metabolize 50% of the absorbed herbicide. So again, we start with corn, which is naturally tolerant, less than 2 hours. This population designated CHR and this one designated SIR are essentially equivalent in the speed with which they can metabolize this group 15 herbicide. The ACR and WUS, these are two sensitive populations. And you can see that it takes almost 50% longer for those two populations to metabolize the same amount of the active herbicide. So how do we piece all this together when we think about soil residual herbicides to manage water hemp and soybean? Well, many times we talk about reducing the selection pressure for the evolution of resistance to our foliar applied herbicides by simply not exposing these herbicides to large numbers of plants. And of course, one way to do this would be to use an effective residual herbicide. They're often referred to as the quote unquote foundation for water hemp management programs. But again, we have to accept the fact that we now are contending with issues of resistance to our soil applied herbicides. Now, it's not always easy to detect that under field conditions. And so we thought it would be a good idea to spend just a couple of minutes to explain how resistance to soil applied herbicides is actually manifest. And so this is a simple graph looking at degradation of a herbicide in the soil over time. And again, on the y-axis, we have the percent herbicide remaining. On our x-axis, we have a measurement of time in weeks. So at week 0, the day that the application was made, we can see that the concentration of the herbicide is at its highest level. And over time, however, it gets less and less. So the concentration in the soil decreases over time. And this is not a bad thing. This is actually a good thing because we want herbicides to degrade in the soil over time. We don't want them to persist into the following season necessarily because our rotational crop could be somewhat sensitive to it. But the concentration over time, as it decreases, we're going to reach a point in the season where the concentration is now low enough that sensitive plants can actually emerge through it. And this is very common. We see this every year. Rarely do we see a soil applied herbicide give us season-long weed control of every possible species in the field. But if this is the concentration where a sensitive biotype can emerge, at what concentration would we expect a resistant biotype to emerge? And of course, the answer to that question is the resistant biotypes can emerge at a higher concentration relative to the sensitive. And so to try to illustrate that, we've got a photograph here of a PPO resistant and sensitive water hemp populations. And this is some work that we did many years ago in the greenhouse looking at flumioxazin or Valor and the level or the amount that it actually takes to control a resistant water hemp or a sensitive water hemp. These numbers in the white text are the application rate. So these pots were sprayed with 3 ounces. These pots were sprayed with 3/10 of an ounce, etc. All the plants in the pot in the back row are from the resistant population. All the plants in the pots in the front row are sensitive. And so I would say 3 ounces, somewhere between 2 and 3 ounces of Valor is a fairly common application rate here in Illinois. But if you ask the question this way, what rate of Valor do we need to actually control a germinating, emerging water hemp seedling at any one point during the growing season? Well, the answer is we don't necessarily need 3 ounces. We only need 0.03 ounces. So if we only need 0.03 ounces, why in the world are we spraying a rate that's 100 times higher than that? And of course, the answer is that one of the goals of our residual herbicides is we're trying to achieve several weeks of good soil activity, good soil residual weed control. So we're actually putting on doses that are so much higher than necessary to control a germinating seedling at any one point because we're hoping to get 3 weeks or 4 weeks or perhaps even 5 weeks of good residual weed control. And so now if we go back and look at this graph, hopefully it's a little bit more clear that when we see resistance to our soil applied products, what happens is that the length of residual weed control gets less and less. So instead of perhaps getting 5 weeks of good residual control of a sensitive population, perhaps now we're only getting 4 weeks or 3 weeks, for example. And these are data that were generated several years ago in Southern Illinois that actually show that when we take something like a PPO inhibiting herbicide applied to a population that is already resistant to PPOs, the frequency of the resistance can change. And so here on the y-axis, they're looking at the change in the frequency of resistance. When there was no herbicide or no PPO inhibiting herbicide, there was no change in the frequency. When they applied only a PPO inhibitor, in this case it was fomeciphin, at either 4/10 or 6/10 of a field use rate, we could see a significant increase in the frequency of PPO resistant plants. Same way when they combined fomeciphin with a group 15 herbicide, or when they selected a different PPO inhibitor. And so folks, this is probably the main reason why we continue to see a fairly rapid increase in PPO resistance in our Illinois water hemp populations. So now to try to wrap this back together. So what is again, the big deal with symmetrical and asymmetrical triazines and these two different types of resistance mechanisms? Well, target site resistance. Remember we talked about there's been a physical change in the target site. That confers resistance to both symmetrical and asymmetrical triazines. So in other words, when we have target site-based triazine resistance, neither atrazine nor metribuzin remain effective. If there's good news in this story, and I think there is, the good news is the fact that the vast majority of our triazine-resistant water hemp in Illinois is not based on target site resistance. It's metabolic. Now, the big difference, of course, is that non-target site resistance, currently that is specific to symmetrical triazines. So in other words, when we see non-target site resistance in our Illinois water hemp populations, atrazine is not very effective, but metribuzin remains effective. So that's one of the key points. And so a couple of years ago, we asked ourselves the following question: how effective would metribuzin be on a water hemp population resistant to herbicides from group 2, from group 5, group 14, group 15, and even group 27? And what we really were interested in looking at was the length of residual control that we could get from a product like metribuzin versus a PPO inhibitor. And so we selected sulfentrazone. And so we did field experiments at this resistant water hemp location in both 2019 and 2020. This is a typical black Illinois prairie soil, 4.4% organic matter. We used the Tricor formulation. Tricor 75DF was the metribuzin that we used, and we applied it at 16 different rates. And those 16 different rates were in 1 ounce increments. So we started out at 1 ounce of Tricor, and we went all the way up to 16 ounces. For the sulfentrazone comparison treatments, we applied 2 rates. One was what we would consider a common use rate of about 1/4 pound active per acre, which is very common in many of the sulfentrazone premixes that we use. And we also selected what we could find or calculate to be about the highest rate that we could apply in any premix, and that was 0.313 pounds active per acre. We applied all the treatments the day that we planted soybean, which was June 10th in 2019 and June 2nd in 2020. Our plot size, we had soybeans in 30-inch rows. An individual plot was 10 feet wide by 30 feet long and included 4 soybean rows. Each of our treatments we replicated 3 times. And the evaluations that we made, we visually estimated water hemp control at 14, at 28, and again at 42 days after planting. And so what did we find over 2 years? Well, let's set up this graph of our results. Here again on the y-axis, we have water hemp control as a percentage on a scale from 0, which is no control, up to 100, which would be complete control. And I broke down our ratings by our time. So we have our 14-day ratings, or 2-week ratings, our 4-week ratings, and our 6-week ratings. And instead of trying to show you 16 different rates of metribuzin, what I did is I grouped the rates together. So the white bars represents the average control that we had for treatments of Tricor from 1 ounce to 5 ounces. The blue bars would be the average control that we had from 6 ounces to 9 ounces. And then the orange bars would represent the control that we had from 10 ounces up to 16 ounces. And we did the same thing with the 2 rates of sulfentrazone. We simply averaged those, and those numbers that you can see at the top of each respective bar. And so if you start out first here at 14 days, one of the take-home messages is what we could see here in the white bar. The metribuzin at rates of 1 to 5 ounces. Many people are reluctant to go any higher than 5 ounces of metribuzin. But even by 2 weeks, we only were around 60% control. But look at the level of control that we were still maintaining at these higher rates of metribuzin. Even 6 to 9 ounces of a product like Tricor, we were still well over 90% controlled in the same way at the highest rate range of 10 to 16 ounces. At 14 days, our sulfentrazone was still hanging on and doing a pretty good job. But look what happened now 2 weeks later at 28 days. The level of control now with sulfentrazone is only about 50%. Level of control with our low rates of metribuzin is not very good, but look again at the control that we were still able to maintain at 4 weeks with these higher rates of Tricor or metribuzin. And then finally out here at 6 weeks, when we were in this rate range, this average control from 10 to 16 ounces of metribuzin, we were still over 90% control of water hemp. And I know sometimes it might be difficult to actually visualize this just based on a graph. So we took these photographs of our work here from 2020. What you're looking at here on the left side, this is the highest rate of sulfentrazone, and this is a plot, soybean plot, 42 days after planting. The photograph here on the right was a trial where we had actually the 16 ounces of metribuzin as Tricor. I think there's a pretty stunning and significant difference that you can see in these photographs. And so what we summarize from this work is that metribuzin can still be an effective herbicide option to give us residual control of water hemp in our soybean, even in populations where we don't get very good control with atrazine in corn. But as it's always been with metribuzin, the appropriate application rates are absolutely necessary in order to try to achieve a sufficient level of residual control. And as we showed, 5 ounces or less is not going to be very effective. But 10 ounces of a trichlor metribuzin type product or higher was still over 90% water hemp control 6 weeks after planting. And the other point, again, really to try to drive home, when you have PPO resistance, this greatly diminishes the residual control with our soil applied PPO inhibitors. In the current work, at 6 weeks after planting, we averaged about 40% control. And I went back and looked at some previous work that we did actually back in the mid to late 1990s, before PPO resistance became very widespread in the state. And at similar rates of a sulfentrazone product at 6 weeks, we were still over 90% control. So again, remember that the way that this PPO resistance is going to manifest itself in the field is our length of residual control is going to be much less. But every conversation that we have around metribuzin, one of the first questions we get is, what about soybean injury? And certainly it is possible. There always have been cautions with using metribuzin in soybeans, and they are still in play to this day. There are still sensitive varieties, but in all honesty, we do not know how common or how frequent these are in commercial varieties. The best advice that we can offer is simply to check with the seed company. Remember that your soil pH and organic matter are important with respect to influencing the amount of metribuzin available for uptake. Availability of metribuzin increases with increasing soil pH. So metribuzin is really not an option that you strongly want to consider when you're talking about soils with pHs, 7, 7.2, 7.4. The higher the pH, the more available it becomes, and the more likely that you can have soybean injury. And there's also has a high affinity for organic matter. And I can say for the 2 years that we conducted this research in the field, we saw absolutely no soybean response from metribuzin. But remember, the organic matter in that soil was over 4%. So certainly be cautious and be studious when you select your application rates, because the metribuzin product labels will break these out according to your soil type and your organic matter content. And as I think back historically about metribuzin damage in soybeans, one of the places in the fields where it was fairly common to see it would be on the headlands or the areas of spray overlap. And if you think about the commonality of metribuzin injury 30 years ago, perhaps even 40 years ago, there's a few differences between that time period and today. And one, of course, is that historically we used higher rates of atrazine than we do today. It wasn't uncommon to run 2.5, perhaps even 3 pounds or more of atrazine. Well, higher rates of atrazine in many cases could lead to atrazine carryover. If we see a lot of metribuzin damage in soybean in the overlap areas of the field, there's a pretty good chance we might have overlapped the atrazine last year. So let's say hypothetically in our corn year, preceding corn year, we had 2.5 pounds of atrazine, and the overlaps were up to 5. And if we overlap the atrazine in corn, there could be a chance that we're going to also overlap the metribuzin this year in soybeans. But I think many of the advances that we have in application equipment have really helped us to avoid a lot of overlaps. And certainly I would argue that today's modern spray application equipment is much more accurate than the old pickup truck sprayers that we had 30, 40 years ago. And the other thing that occurs in our soils now, and I admit we really don't know how common this is, but we have a phenomenon called accelerated atrazine degradation. And this is simply an example of what this would look like. This is some published work that looked at atrazine degradation in soils collected from Iowa, Illinois, and Pennsylvania. And the soils were collected either from fields that had no history of atrazine use or had a long history of atrazine use. And so if we look at the representative Illinois soil right here, this number is the amount of time it took for 50% of that applied atrazine to degrade in this particular soil. It only took 2.5 days. If you look at this soil from Iowa that had no history of atrazine use, it was closer to 48 days for half of that atrazine to be degraded. So along with much better application equipment, I think the contribution of atrazine as more or less synergizing metribuzin damage in soybean, I would argue it's less likely to happen today than what it did several decades ago. And finally, just to reiterate, when it comes to soil applied herbicides and soybean injury, there are many different types of soil applied products that can cause injury. What you see in this particular slide is damage from one of our soil applied PPO inhibiting herbicides. It's been very, very common across Illinois for the last probably 5 to 6 growing seasons. And again, another example of injury to the cotyledon leaf from our soil applied PPOs. So injury, soybean injury from metribuzin, it's not the only type of injury that we can see and that we have encountered. And with that, that's the end of the presentation. And I'd certainly want to take the opportunity once again to thank you for your time and for your attention. And I do wish everyone a very safe and prosperous 2021.